So we said that there's this crystal structure that was shaped like this. Okay, and this distance was D, that we were putting into this formula. Okay. And our formula, of course, was 2D minus theta, the incoming, and lambda out, some multiple of the wavelengths in that tells us. So we have destructive or destructive interference. All right, so this is D, and then when we rotated, then all of a sudden we had D on a side like this. And most of you already said that, all right, so then D1 is equal to whatever D is, and then the new D is equal to D over root 2. And this just magically appeared. I'm really fascinated how you guys necessarily got this. So I just wanted to go over the geometry. Maybe you guys are quicker in geometry than that. That's quite possible. If this is our D length here, when we rotate, then this is our D length now right here. No. I didn't tell lies. This is D right here, and this is D right here. What we need is this height right here, okay, which is half this cross-section line. Now we can do this a couple of different ways. We can take the whole side like this, and note that we've got a triangle here that's D, and this side over here I'll just call A for no other reason. Okay. And note that what I'm interested in, D2 is equal to A over 2. So this is how we're going to go about trying to find that. So just use Pythagorean theorem, and we'll say that A squared is equal to D squared plus D squared. So we have A is equal to the square root of 2D squared, which is equal to the square root of 2 times D. Yeah, now we said that D2 is equal to A over 2. Lovely. So we're going to say that D2 is going to be equal to the square root of 2D over 2, which is another way you can write that. Yeah, if we put this in proper notation, this is the way to write this. This is the improper fraction. So I don't know, maybe you guys are just better at doing math, but I was surprised to see that also this was just written down and this was in here. I am toying with putting this one on the test. I got to get your assignment ready. I want to make sure I do that first before I even start working on the test. I will probably start tonight. I don't know if I'll get it done. Chances are very slim. If there is anything else, any pointers or anything that I need to get to you guys, I will email you at your Shawnee email address. Does everyone actually get their Shawnee email? I don't know. All right, so that was the first thing. It's just figuring out, and then you put this back into here, and you figure out the rest of this. Now, the other parts that I want to talk about this in was 416, Part B. 416 talks of Bragg diffraction experiment conducted using a beam of electrons accelerated through 1 kilovolt potential difference. Blah, 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 blah. It went well. But Part B says, if a beam of X-rays produces the diffraction maxima at the same angles as the electron beam, what is the X-ray photon energy? All right. The thing that concerns me about this is you guys got it right, but had it been in the reverse, you would have gotten it wrong.
Which one is this?
416b. All right, it's the exact same equation right up here, the 2d sine theta. Okay, there's 2d sine theta. All right, so you go and you solve all of this, and you get some sort of answer. And some of you did, some of you didn't come up with the idea that the wavelength here that was necessary for the electrons was 0.388 nanometers. You didn't necessarily even need to do this to figure out the answer. Yeah, this is the one that I went through and did all with special relativity. Even the part you missed, I redid all of your homework set in special relativity, thinking that you guys had done it wrong, finding out that the difference was stupid small.
See, that's what I thought after I turned it in, and I forgot to do the other one.
So it's fine. So I'm changing it to 10% instead of 1%. Because the answer for this one, this was the speed of the particle u, right here, this is the one I was referring to, 1.87 times 10 to the 7th meters per second. And I do believe the correct way to do it brings it to 715 or something like that, whereas if you did it your way, if I remember correctly, it's 875. So we're talking 0.00 It's the array to the 4th decimal place before it makes any difference. And that's at 6, this is 6% C, so it's a sizable portion. So we're going to change our limit to 10% C. And I'll make sure that your homework, that your test reflects that. So if you get a number that's greater than 3 times 10 to the 7th, then you need to switch, because then the relativistic effects should start to be at least non-negligible. Right, in any case, and you came up with an energy. All right, what was the first part you were trying to do? You were just trying to find the speed, right? The first part? Part A. Okay, part B says, a beam of X-rays produces a fraction maximum at the same angles as the electron beam. What is the X-ray photon energy? And what all of you guys did is then you sit there and you took that and like, okay, well, I'll take the energy of the electrons and just find that. And you found the energy of the electrons and said that that's my answer, that that has to be the energy of the photons. Well, it turns out that's true, but that's by sheer luck. If I wanted to know, in this case, it does go this direction. The energy of the electron is going to be equal to the energy of the photon for this. But the only reason that's true is because how do you figure out what the energy of a photon is? What's the equation of it involving Planck's constant?
B equals H Planck's constant squared divided by 2m³ and then 2 squared.
Oh, you're making this more complicated. You actually did it right, I do believe on this one. No, we can just say HF.
Well, I have a question.
Or we can say HC over lambda. The point being is that the energy, go ahead.
There's a 1.87 in this thing somewhere?
The answer, I believe, is 1.87 for this speed.
I don't think we're that wrong.
Well, I'd be happy to take more points off your homework.
No, but I'm confused. Like, where was this supposed to be at?
Is that speed?
Oh, no. You did do this. You skipped. You did it right in the sense that you found the wavelength and used the wavelength to come up with the angles that are associated with it.
Okay.
You did it the way I did it. And I like that approach. So you're fine.
Well, sure. It's going to be another equation in the book. that
In
actually
any
works.
case, which also helps you for the next part because you instantly jumped to this equation to solve for this. The point being is that in this, for the Bragg fraction, it wants to know the photons that would work the same as the electrons. Let's go back to the original equation. Here's the equation. So what has to be the same for the photons that was the same for the electrons, for the same equation to work? What's the only variable in this? Lambda. It's the wavelength. So what you guys did was you compared the energy of the two particles. Now it worked out well because if I was going to do a photon, photons are only a function of their lambda. So no big deal. But if I go into the mass of another particle, so if I go into a different particle, I said a photon compared to a double photon, or say I invented something that had 2 mass units or something like that, 2 atomic units, then you can't just compare the energies because it's not saying the energy has to be the same. It has to be the wavelength that's the same for this equation. Is everyone kind of following me in this?
So this is working the way or not?
Say it. You did it the right way, David, yes.
Okay, so it's working the way though.
In this problem, because it asked about photons and not particles that have mass.
Okay.
Most particles that have mass, they're not purely a function of the wavelength,
Okay.
like this one is. So this one did work, and I didn't mark anybody wrong for it, but I wanted to make sure you guys understood this. If you're going the other direction, you're looking for a particle that has mass, you can't. You're looking for the same wavelength, you can't assume that the energies of the two particles that have mass are going to have the same wavelength. What do you got?
Okay, so on 416 for mine, like what, I don't really know. You said what about the rest? Is that part A or part B?
No, this is for part A. It says find all of the angles. You found the very first one, I think there's 6, all the way to 75 degrees.
Okay.
Yeah. And then part B is just the one we're talking about right now. For the rest of it. Okay. I hope everybody followed me on that.
How do you know how many angles there are? Say, or?
Until sine crafts out on you. So basically, you keep going this all the way until sine will give you an undefined, because you'll get over 90 degrees and then it just kicks back on you. So this is your multiples right here. This is the number of multiples of wavelengths that you could possibly do this at an instant angle. So you could do this a whole bunch of different angles and still find constructive interference and keep going until you're at a point where you're over 90 degrees. So you can't have an instant angle over 90 degrees. Then all of a sudden you're less than 90 again from a different side.
Okay, so which number was I just plugging in and kind of different?
You were automatically assuming m equal to 1.
That's like at the first one, but how do you get
M equals 2.
Oh, just,
n equals 3, n equals 4, up until the graph's out.
okay.
No, but that's a good question. These are the type of things I want you guys to ask. Because if there's things you don't understand in the homework, obviously it's going to be tough to see when it comes
Did you not grade this one?
up. No.
Okay.
I'll explain it. Okay, the other thing I want to talk about is just, I want to watch that video and I want to talk about the implications of it. So we'll watch the video first.